Society of Physics students here at Marshall University. First off, I want to thank Marshall University, the College of Science and the Physics Department. They've always been very supportive of anything that Society of Physics does. And I want to really thank them for everything that they do to support the student organization here on campus. Also want to thank Ellie White and Jackie Sizemore for doing a lot of the work to put this speaker series together. They've done a fantastic job. They're really spearheading this effort and they're doing just a fantastic job. So I want to tell you a little bit about Marshall University Physics Department. We have 10 faculty. We have 6 that are active in research, from theoretical condensed matter to water filtration. Marshall University as a whole is around 12,500 students. There's around, well, I can tell you there's many programs very partial to physics, of course, but it just recently became an R2 doctoral university. So in terms of physics, we have a BS and an MS program here in physics. So if you're interested in physics and understanding how the world works and everything around you, shoot me an email. So my email is mcbrides@marshall.edu, and I'd be happy to answer any questions you have about the physics program here. So again, we do have a bachelor's and a master's in physics, and we have 5 areas of emphasis: physics, applied physics, biophysics, medical physics, and the new area of emphasis in medical imaging. So again, if you have any questions about those, just shoot me an email and I'll be happy to have a discussion with you on Zoom, or just email back and forth and answer your questions as well. But with that, I think I'm going to turn it over to Ellie White, and she'll have a couple words to say about our speaker.
Yeah, thank you so much, Dr. McBride. So yeah, Marshall Physics Department is a really cool place. So thanks for sharing some information about that. Yeah, so I also wanted to thank everyone who's here for coming to the second talk in our Faces of Physics speaker series. So I am really looking forward to listening to this talk by amazing researcher Karen Perez, whom I'm going to introduce very soon. So after the presentation, just a heads up, like last time, if you were here, we'll have time for a question and answer session, and we welcome you to share your questions via the YouTube live chat, or you can post them on Twitter by tagging our handle, which is @MUPhysicsClub. So if you enjoyed this talk, we hope you'll join us for future installments of the series. Dr. Brian Kent Wallace of Fisk University is our next speaker, and he'll be joining us at 7 p.m. on January 20th to talk about his work in physics education. And Dr. Abel Mendez will be speaking at 7 p.m. on February 16th for a talk on habitable worlds. So many more speakers will be announced soon as well. If you'd like to receive email updates about upcoming events, we'll be sharing a link in the chat where you can go sign up. And now I'm honored to introduce Karen Perez, who I was lucky enough to hear speak this summer on her research on SETI, or the Search for Extraterrestrial Intelligence. Karen actually received her bachelor's degree from Cornell University in 2019, and she is now a second-year graduate student at Columbia University. She's studying pulsars across different wavelengths, including radio and X-ray. And she also works with the SETI Breakthrough Listen team at UC-Berkeley, searching for technosignatures, or signs of intelligent extraterrestrial civilizations using giant radio telescopes. And she's going to be telling us all about her incredible research this evening. So I'm going to turn things over to her right now so we can get started. So thanks again to all of you for coming. A special thanks to Karen for making the time to share her work with us today in the midst of her busy schedule.
Okay. Hi, everyone. My name is Karen Perez, and like Ellie said, I'm a second-year grad student at Columbia, studying pulsars across different wavelengths. But I also work with Breakthrough Listen team and my advisor, Vishal Gayar, over at UC-Berkeley, looking for technosignatures using these giant radio telescopes all across the world, looking for these signatures in the Galactic Center. And we recently submitted a paper on this, and this is what I'll be talking to you about today. So before I start, I do want to thank the Marshall University Society of Physics students for putting this series of Faces of Physics together. And I'm really happy to have been invited, as I am only a grad student so far. And I hope that everyone here today enjoys the talk today and goes to the rest of the talks in their upcoming series. I also do want to say that it's a bittersweet day, because although I'm really glad to be giving a SETI talk today, I'm also saddened at the news earlier today about the collapse of the Arecibo telescope in Puerto Rico. And for those of you that don't know, the main cable of the telescope broke earlier in November, and the National Science Foundation had planned on closing the telescope because the damage was too much and it posed a safety risk to fix it. But unfortunately, this morning we all woke up and we saw the news that some more cables had broken, and the 900-ton instrument that you can see on the left here just like collapsed down towards the 300-meter dish antenna. So it's a very sad day for the astronomy community. And I never got to visit the telescope, but Arecibo was actually used for various SETI searches back in the day. And so it has a very special history with SETI. And some of the data that was collected years ago of nearby stars is still being analyzed today with SETI at Home, which is a software that you can run from your very own computer to help us look for ET signals. But there are still other radio telescopes in the world, so we can continue trying to answer this question of where we are alone in of whether we are alone in the universe. So there are currently about 4,000 exoplanets that have been discovered so far, and about 50 of those are Earth-sized and they're inside the habitable zone. So this means that they're inside a region around the star where a planet might be able to host liquid water. So telescopes like the James Webb Space Telescope, which will hopefully finally launch soon, sometime later in 2021, I think, will aim to look for these biosignatures in the atmospheres of planets, like oxygen or ozone, which could be indicative of life, assuming that ET follows the same biology that we do. But these kinds of telescopes will only be able to observe a few stars and not search for biosignatures across the entire sky. So these telescopes, they could help find, for example, like bacterial life, but like what about intelligent life? So we don't know the signs of ET, but we can try and find intelligent life by thinking about how we would detect our own technology. So if we look at the electromagnetic spectrum, which is this entire thing covering a large range of frequencies, if we look specifically at the radio spectrum, radio waves are the easiest to generate and can travel farther distances without them being absorbed by the atmosphere. So we think that radio waves would be the best way to detect any evidence of intelligent life. So here you can see how the atmosphere hides most of the other wavelengths in the spectrum. And just to give you an idea, radio waves are generated from things such as cell phones, microwaves, aircraft radar, and so on. So GPS satellites, all of that stuff. So here we're looking for two types of signals. We're looking for deliberate beacons, which means that these signals could be purposely transmitted for our detection. So like radio waves from ET would look different from radio waves produced on Earth because they would be so much brighter, they would be stronger, and they would also look very differently than radio waves produced naturally. The second kind of thing would be to look for leakage radiation that we might be able to pick up from their own transmissions between ET. But these would only be able to be detected for a few light years because they are very weak. But we're looking for these two types of signals. So how do we search for these signals and where do we start? So thanks to Breakthrough Initiatives, which is a 10-year $1 million program to search for technosignatures, we're able to look for these ET signals. And they make all their data accessible to the scientific community and the public. They have over half a dozen radio telescopes and other optical telescopes around the world today used to look for these signals. And some of their targets include 1 million nearby stars, 100 nearby galaxies, and deep observations of the galactic center and the galactic plane. So the galactic center is what I'll be talking about today, as I said already. But before I describe how to search for these signals, I want to show a small video of how a signal would come about. Let's see if this plays. Yes. So this is like the Milky Way galaxy, for example. So here we are starting to detect like radio waves coming out of civilizations. So now we zoom in on like a planet like Earth, for example, or Earth-like planet. You can see that life begins and intelligent life develops, then technology. Then when this technology develops, then they might be able to develop a radio signal. And this radio signal will like propagate all across the universe to the point where we might be able to detect it at some point. So this is a really cool video that my advisor Vishal Gayar showed me, and I really like this interpretation of it. So you can see that they start producing radio signals and they propagate. So the question now would be whether any civilization out there has produced any strong radio waves that we could detect. So here we see, we used a Green Bank telescope in West Virginia and the Parkes telescope in Australia, which you can see right here. So it's just really cool to think about how a civilization out there could be producing radio waves, or could have produced a radio wave a long time ago that we might be able to detect it today. Yeah, so now I'll talk about one of the main targets of the Breakthrough Listen, which is to survey the galactic center, like I said, across the widest radio frequency range ever covered, and look for signs of intelligent life by searching for both narrowband signals, which means they cover like a very small frequency range, and broadband signals, which means they cover a very large frequency range. So we'll be using these two telescopes, the Green Bank telescope in West Virginia. It has a 100-meter antenna dish, and it covers about like the size of 2 football fields. And then the Parkes telescope in Australia, which has a 64-meter antenna dish. Yeah, so why are we looking towards the galactic center specifically? The line of sight towards the galactic center has the largest number of stars in any given direction. It's also a potential location for an intentional beacon built by advanced intelligence, and it's the most energetic region in the Milky Way. So taking the first point of the galactic center having the largest concentration and highest number density of stars within our Milky Way, these stars have had a longer time to develop habitable planets due to the inside-out formation of our galaxy. And because of this, these planets have also had a longer time to develop intelligent life. As you can see on this figure on the left, plotting the fraction of stars with a habitable planet versus radial distance. So you can see that as we get closer to the galactic center, between 0 and 2.5 kiloparsecs, as many as about 10% of stars can have at least one habitable planet. So the second point uses the Schelling point idea from game theory, where the point in this case is defined as a solution where if you have two sets of people, or in this case civilizations, if they want to meet up somewhere but they can't communicate, what would be the default place or location to choose? So an example of this is if you and a friend are trying to meet up in New York City, for example, and there's no way for you to communicate, where would you meet and at what time? So in this case, the most likely scenario is that you would probably meet at noon at Grand Central Station. But we can use this idea of the Schelling point and apply it to search for intelligent life, where we have this large amount of space that we can't cover, so we must narrow down our search. So we look towards the galactic center for the reasons mentioned earlier regarding it being the most likely region to host intelligent life, but also for the fact that the galactic center is the center of the entire galaxy, right? So it has to be the likeliest region for a civilization to put a beacon on the galactic center or near the galactic center, since it would maximize the detections across the entire sky. So there's no better place in the center of the galaxy. So past surveys like Shostak and Tartar have produced short searches for narrowband signals that only cover a very narrow bandwidth range, such as specifically only looking at like the 21 centimeter hydrogen transition line around the 1.4 gigahertz frequency. But this survey will be the first to cover a wide range of bandwidth at a high sensitivity, producing high resolution data products. So like I said, we'll be using the Parkes telescope in Australia. We'll cover about 350 hours of observation there, between the frequency range 700 megahertz to 4 gigahertz. And then we'll use the Green Bank telescope, where we'll look from 4 gigahertz to 93 gigahertz for about 280 hours. So in total, we'll cover about 100 gigahertz of frequency range, and we'll observe over 600 observing hours. So our observing plan includes using the ultra wideband receiver at Parkes to cover the lower end of our frequency range, like I said, 700 megahertz to 4 gigahertz, as well as using 7 different bands in the Green Bank telescope to cover the rest of our frequency range. So for each band, we will do both deep observations of the galactic center bulge, as well as shorter on-off pointings around the bulge. So the longer observations are going to be used to look for both physical and artificial broadband signals. So like pulsars or any signals from ET that are just wider. And we will use the shorter observations to look for narrowband signals. So far, we've completed observations of C-band between 4 and 8 gigahertz, and the analysis part as well. We've completed all the short 5-minute on-off observations, but we still need 2 more hours of the long observations. And we've also completed the first 14 short pointings of the Parkes telescope, which I'll show later on. So now to search for narrowband signals in our data, we use SETI, which is a breakthrough listen code designed to look for narrowband Doppler drifting signals. Where here a beacon is taken to be a continuous sine wave transmitter. And we channelize our data to about 1 hertz to optimize for signals. Oh yes, so I will get back to this histogram later, but first I want to talk about the actual pipeline. So we search for parameters such as this SNR, signal to noise ratio, and drift rate. But because searching through the entire parameter space is very computationally expensive, here we choose an SNR of 20 and a drift rate of plus or minus 4 hertz per second. So we're focusing on the green part of this pipeline right now. The rest will come later. So if we go back to this histogram here, you can see all the hits found as a function of frequency for both telescopes, the orange showing the Parkes telescope and the blue showing the Green Bank telescope for our full 16 hours of observing so far. And keep in mind that these are the total number of hits across all of our observations. So we have about 2 million hits total. But now to identify the signals from these hits, we apply an on-off method to identify interesting signals from RFI, or radio frequency interference. So like I said earlier, these could be like microwave signals, radio signals, cell phone signals, aircraft radar signals, and anything that might be interference. So now we're moving on to the second half of this pipeline. So by choosing an off pointing for each on source and alternating between the two on, off 3 times for a total of 6 observations. So here we have 1 on, 1 off, 1 on, 1 off, 1 on, 1 off. We can identify any possible signals in our data. So this method helps us remove any RFI from Earth-based sources, like I said, cell phones or anything aircraft radar related. But a true signal would only appear in the on sources, as you can see here, and none of the off scans. In addition to this, signals due to RFI would appear showing no Doppler drift due to originating from a terrestrial source. So they would appear as a straight vertical line. Whereas a true signal from outer space would, whether it's from a satellite or something else, would have some Doppler drift due to the relative difference in velocities between the transmitter and the receiver. So an ideal potential ET narrowband signal would look like this. It would appear in all the on scans, but none of the off scans. And it would be non-zero drifting. And we'll look at some of these examples later on. So here we have our observing plan for the C-band Green Bank telescope, where you can see an example of the 5-minute on-off pointings. So here we labeled the galactic center as A00 in the middle, the red circle. And we have a set of 3 instead. So we'd have 9 observations in total. So we'd go like C07, A00, C01, C07, A00, C01, and then repeat that pattern one more time. So and the reason why we keep like a beam away from each other is to avoid any double detection. So if we were to use these 2 beams, for example, we might find the same signal on this beam and this beam, and then we wouldn't be able to know where it came from or like decipher it correctly. So we want to make sure we avoid any double detections. Similarly, for the Parkes telescope, you can see, so yeah, you have a lot more pointings for the Parkes telescope. For C-band, you only had like 2019, I think. And then for Parkes telescope, we have 375 pointings. So this will take a lot more time to go through. But you can see the galactic center bulge in the center again. In the middle of the diagram, the galactic center is labeled as A1. And the dotted line circle around just denotes like the half power beam width. So it means that if we want to move far, if we don't want double detection, we have to move far away from those sources. So here the pointings labeled A1 through A7 are the on sources, and the ones labeled B1 through B7 are the off sources. So like I said, we want to make sure that we are a whole beam away to avoid double detections. So like A1, B1 would be a pair, A2, B2 would be a pair, and so on. So now that you know how the observing plan works, now we can go back to our turbo SETI code. So now we're looking at the green part on the right. But I do first want to remind you that before doing this on-off detection, we did have 2 million hits to start with across all of our short 5-minute observations for Green Bank, and then for Parks we had done 10-minute observations. So this is covering all of our observations so far. But now that we have all of our hits for a pair of pointings, we can do the on-off comparison to find events which are non-zero drifting. So we want to remove all those that originate from Earth, right? So any zero drifting events get removed, and then we filter them as filter 2 and filter 3 requirements. So filter 2 here means that the signal was found in one of the on observations, but none, in at least one of the on observations, but none of the off. And filter 3 would be ones that were found in all 3 on observations, but none of the off. Yeah, so after this, we can plot our candidates and then vet them through visual inspection. And there was a lot of candidates to vet through visual inspection, actually. But before I show you any of the interesting candidates, I just want to show the following histograms where sorry, where we show all of the events as a function of frequency. So here you can see the filter 2 candidates in orange from the Parkes telescope, and the Green Bank telescope in blue. The filter 3 candidates are shown in red for the Parkes telescope and for black in the Green Bank telescope, which we don't have a lot of them. But you can see this green circle on the right, which I'll come back to later on. It's just important to like make note of it right now, because it's very interesting to see that, like, unlike all the other bins in this histogram, this is like the only detection that we make at that frequency range. So a lot of the others might be disqualified as RFI, but this is like very unique. So this next histogram shows the number of candidates as a function of drift rate. So as mentioned earlier, although we try to remove drift rates that were zero because they were probably like due to terrestrial sources, some events with drift rates close to zero still got through. So in the future, we'll make sure to account for that. Oh, sorry, I forgot. This next one takes a while to load. Oh no. Okay. So this is a scatter plot between the drift rate and frequency of all the events that we found. As you can see on the right-hand side, the legend, filter 2 and filter 3 events. So this just helps us see the distribution of events that can be ruled out as RFI across different frequencies due to having drift rates very close to zero. So like in the case where we find a very unique event, we can look back at this diagram or any of the other histograms and see whether there were any other hits at that frequency that we can compare our signal to. So here are some examples of RFI detected. So these are the on-off plots that I was talking about. This is from like our actual Galactic Center data. So here we're looking at the C05 pointing. So this is the on source, and then C03 is the off source. But here we can see example of like very clear RFI because it is shown in all 6 observations. Same thing on the right, you can see this straight line right here. And then you also see this weird triplet pattern, which does kind of only appear in the on observation, but then sometimes it shows up on the off observation. And because it shows up in the off observation, this is why we can also vet this candidate out, because any potential ET signal would not be showing in the off scans. So it's most likely due to a terrestrial communication signal. So here we have an ideal signal, like we discussed earlier. It's non-zero drifting and is showing in all the on observations, but none of the off. So you can see it's showing panel 2, panel 4, and panel 6. But we find that this frequency of 1.38 gigahertz matches that of the GPS satellite Navstar. So unfortunately, it's also due to RFI, just RFI that's like harder to detect because when you see something like this, you want to kind of make sure it's not, you want to vet it out, right? So what we did, we went into like the satellite database. We tried to find any satellites that might be happening at similar frequencies, and we found this. So we bet it out due to likely being a terrestrial origin, but it's a very good depiction of what we expect a potential ETI signal to look like. So these last two candidates are interesting because they are both experiencing high drift rates. As you can tell up here, we have like negative 0.18 and negative 0.66. And the one on the left is happening at 4.2 gigahertz. But it's actually, it's a very interesting candidate, but if you go back and look at the histogram is very populated with hits around that frequency range. So this tells us that it's probably RFI again. And the frequency, the signal on the right emits at the frequency of 6.4 gigahertz. So this is a very unique signal. This is the one that I circled earlier, the green circle at the bottom. It's only seen once in all of our observations. So it's a very interesting signal, but since it does not repeat on the on observations, we also bet it out due to probably being due to some intermittent terrestrial source. So these are probably the two most interesting signals that we found from our 16 hours or 18 hours of observation data so far from the Galactic Center. And another type of signal we're looking for, I mentioned earlier, so now we looked at narrowband signals, and we're looking at wideband signal searches. So these wideband signal searches spread over larger frequency ranges, as you can tell by the name. Typical physical sources show a positive signal in frequency and time. So like pulsars, which if you don't know, they're really fast rotating neutron stars in the universe. Fast rotating stars in the universe would appear like this in the frequency and time plot. And the positive dispersion measure just points to like the dispersion measure is like basically like the number of electrons between you and the pulsar or the source, like basically the amount of plasma or stuff that's between you and the source. So we think that ET might know of this natural signal, and if ET knows that these pulsars produce this physically natural signal, they might be able to produce an artificial signal, which could be flipped across frequency, flipped across time, or flipped across both frequency and time. So we would call this a negative dispersion measure. So we look for these types of signals as well. And there's a pipeline which we use to look for these signals produced by advisor Vishal Gayar. It's called SPANDAC. The way it works, you give the data to the pipeline. It checks whether it has a negative dispersion measure, as I mentioned below. And any signals with positive dispersion measure would be due to a physical source, whereas anything with a negative dispersion measure would be due to an artificial source. So we check for negative dispersion measure. If it doesn't have a negative dispersion measure, then it's probably, like I said, physical or pulsar FRB. But if it is flipped across time or frequency or both, we continue down the pipeline as well. We try and see if they're RFI. Like I said, there's a lot of radio frequency interference out there. And then we eventually plot the candidates and also visually sort through them to try and find if we detect any of these signals that I mentioned. So yeah, I guess we've reached the conclusions. The conclusions are that Breakthrough Listen, Galactic Center Survey will look for advanced intelligence using both the Green Bank telescope and the Parkes telescope, covering the widest radio frequency range ever covered for a SETI survey, so between 700 megahertz and 93 gigahertz. And we'll be doing deep galactic center pointings, as well as the regions around the bulge of the galactic center. So far, we've completed the C-band observations, and other bands will follow from the Green Bank telescope. And all this information is in a paper that me and Vishal Gayar recently submitted, and hopefully it will be out at some point. But in conclusion, spoiler alert, we did not find any strong evidence of narrowband or wideband signals yet. But we still have like many more search parameters left to analyze and many hours left to observe. So this is data that we'll be continuing to look at iteratively as better methods and pipelines, which a lot of the other people in the team are working at, as better in methods and pipelines that are less computationally expensive are developed. And to give you an idea, I think Breakthrough Listen like observes about 2,000 hours a year. So that's a lot of data. We have like terabytes of data, and we do need just better pipelines to analyze all of it. So yeah, I guess if there's any questions or comments now, I can take them. It's a shameless promo right here of follow MU Physics Club for future talks. And yeah, I leave with this last quote, which a lot of people ask, like, why are we looking for ET, right? And this is like a famous paper from Cucconi and Morrison, which at the end of the paper, they say the probability of success is difficult to estimate, but if we never search, the chance of success is 0. So you have to search, otherwise you'll never know. Yeah, and that's it.
Awesome. Thank you, Karen. Very informative. I really love how all the bullet points were little telescopes. It was very cool. We'll go ahead and leave that last slide up just so if people want to follow you or anyone else on that list on Twitter, they can. So we're going to get into some questions. But before we do that, I just want to remind everybody that if you would like to sign up for email updates for this speaker series, I'm going to go ahead and send the link in the chat now. That way you can stay up to date and always know where to find these talks at. And also I wanted to thank all the people last time that donated to help support this event. We are accepting donations, and if you donate enough, we will interview into a chance to win a 45-quart Yeti cooler. So if you're interested in donating, you can send me an email at sizemore85@marshall.edu. I also threw that in the chat too. Okay, so first question, Karen. This is from Daniel. He wants to know if there is any news on the future Europa probe. Do you know anything about that?
No, we don't really look at, yeah, I'm not the right person to ask for that. I think that would be more like on the exoplanet instrumentation side of things. We don't look at the, like Europa.
Okay. I think there are some
Sorry,
talks
Daniel.
on exoplanets coming in the future too. So, all right.
Yeah, but
Next
I guess that would
question.
be more on like the biosignature side. So they're like looking for like water, like traces of biosignatures in exoplanets, or in this case, it's not an exoplanet, it's a moon. But yeah, I guess what we're looking at mostly would be like technosignatures beyond the solar system.
Okay. All right. Thank you. Still waiting on some questions. Apostolos says, thank you very much for your excellent presentation. Very interesting and informative. Dina White says, thank you. That was a great presentation, and I learned a lot about how the search is being conducted. So, all right, we'll wait a couple more seconds to see if anyone else has any questions. They are a little bit behind in the lagging. Daniel said, I'm studying to be an astrobiologist at the cell and organic chemistry level. So,
Wow.
Little insight as to why they asked.
Yeah, maybe
Okay.
we'll need you in the future once hopefully the telescopes like the James Webb Telescope detects any biosignatures out there.
Yeah, cool. Okay, so here's a question. Is the Breakthrough Initiative an international collaboration?
I don't think it's an international collaboration yet. I know that there's members of the team, like my advisor Bishal Gayar, that are like working with like the Sardinia Radio Telescope in Italy, people over there and people over at the FAST Telescope. But I don't know that we're like getting data, like sharing data from them or anything yet. But like I said, our data is open to the public. So in that sense, anyone around the world is open to use the data and try and find ET themselves.
All right, thank you. Peter wants to know if you know of any updates about the phosphine molecule signature discovered on Venus.
No, I don't really have any updates besides whatever's been published. I think the original authors like tracked back what they had said as more analyses is being conducted, like more careful analyses. Yeah, I know there was a lot of discussion around that, but I haven't really been following it closely.
All right. Another question from Daniel. Have you ever worked with a transgender scientist? I'm transgender and Latino. It can be lonely in the science building sometimes.
I don't think I've worked with a transgender astronomer before or scientist, but I know that like, so I go to school in Columbia, in New York City, and there's like various institutions around that they collaborate with, like the American Museum of Natural History and the CCA, Center for Computational Astrophysics. And just because I haven't worked with a transgender person doesn't mean that there's not transgender astronomers out there. And I think in general, the astronomy community is very welcoming. And going forwards, I feel like it's only getting better. More diversity is being welcomed across all departments. So I think it's definitely something that I think like it's a very touchy subject, but I feel like it's definitely something that at least like the older astronomy community is learning to accept as time goes on. And yeah, I mean, I'm also Latino, so I do feel like, yeah, like I said, diversity is just increasing in general across the astronomy spectrum. So hopefully by the time you are in college or grad school, things will be a lot better.
All right. Well, thank you very much, Karen, and thank you to all the viewers that have joined in tonight. I think this was pretty successful. Also, thank you to the American Institute of Physics for funding this program a little bit. Oh, we got another question. Okay. How computationally expensive are the SETI pipelines? Have they gotten any better?
Yes. So I started working with Breakthrough Listen about like 1.5 years ago. I don't know that they've gotten any better while I've been working with them. But like to give you an idea, like this is something that I'm constantly working on and other members of the team are working on. But to give you an idea, like the histogram that I showed earlier, where we have like 2 million hits for like our 18 hours of data, like combined just, sorry, it's not this one. Combined, like just getting all these hits or finding these hits in all our data probably took like a combined total of like running the pipeline like a few weeks, maybe, I want to say. If we ran the pipeline for each observation at the same time, it would probably be done in like 9 hours. But because we can't run them at the same time, we have to wait till one is done to run the other one. That's why it takes more like a few weeks for just like this set of 18 hours of data. Yeah, so that's why we're trying to like employ like machine learning methods in the future to try and decrease the time that it takes to run these pipelines.
All right, cool. All right, Ellie, do you have any closing comments you'd like to make or anything?
No, other than just thank you again so much, Karen, for your time this evening. I know it's a busy time, and really enjoyed your talk. It was super cool. So thank you.
Cool.
Thanks, Karen.
Thanks for having me.
All right. Well, we'll see you guys on January 20th. Again, sign up for email updates if you want to be up to date on everything that's going on in this speaker series. Yeah, have a good evening, everybody. Bye-bye.